Here's another example of finding area in polar coordinates. Let's find the area of the region inside both of the curves r equals 2 sine theta and r equals 2 cosine theta. As always, it's a good idea to start by graphing the curves. For r equals 2 sine theta, we know that when theta is 0, sine theta is 0, so it'll be down here somewhere. When theta is pi over 2, that is pointing directly upward, sine theta is 1, sine pi over 2 is 1, and 2 times that is 2, so let's have a height here of 2, and we're going to reach this point. And actually, we already know, because we've looked at this kind of curve in class, we know that what we're going to get is a circle that is resting on the origin, that is tangent to the x-axis at the origin, with a radius in this case of 1 and a center at the point 0, 1. Meanwhile, for r equals 2 cosine theta, we're also going to have a circle, but this circle is going to go through the origin and is going to hit the x-axis at 2, and it's going to be a circle that is tangent to the y-axis at the origin. Looks more or less like this. Now these two circles have the same radius, but they have different centers. They do intersect. And we're looking for the region that is inside both, where they overlap. The center of the Venn diagram that we get here. So here are these two regions. And the part that we want is this part right in here. That's our desired region. So we know that we want to set up an integral to find the area of this, but what integral should we do? Well, it's important to figure out which curve or curves are bounding the region that we're interested in. And the situation we have here is that for different values of theta, we have different parts of the curve, different curves with different functions bounding that region. So when theta starts off at 0 and goes out a certain ways, the blue curve is the curve that is bounding that region. We have this region in here that is bounded by the blue curve. Later, for larger values of theta, going up to pi over 2, here's pi over 2, the green curve is what's bounding that region. So we need to actually find two separate integrals. We need the integral from 0 to some value of 1/2 r squared d theta, plus another integral from some mystery value up to pi over 2 of 1/2 r squared d theta. And for that first integral from 0 to whatever the mystery value is, that r is going to be the blue curve. For the second integral, going up to pi over 2, that r is going to be the green curve. We do need to find out what that mystery intersection point is, which is not too hard to guess because this has a lot of symmetry to it. These two circles both have the same radius. So we should be able to figure this out. In fact, we could probably guess right now that at this point of intersection, our theta is probably halfway between 0 and pi over 2, which means it's probably pi over 4. But let's check that. So to check that, we need to find the value of theta that causes the radius, the r, for both curves to be equal. So let's set them equal to each other. Let's say that 2 sine theta equals 2 cosine theta. We can solve this by dividing both sides by cosine theta, or by 2 cosine theta, in fact. So we'll have 2 sine theta over 2 cosine theta equals 1. But actually, this really means the 2's cancel out, and sine theta over cosine theta is equal to tangent theta. So what values of theta cause the tangent to equal 1? Well, we know what those values are. Those values are pi over 4, or any multiple of pi plus pi over 4, but pi over 4 is the angle we want. So our theta does equal pi over 4. So in fact, this mystery bound, the upper bound for our first integral, is pi over 4, and the lower bound for our second integral is also pi over 4. So we should be ready to go here. We should be able to set up both of these integrals and solve them. So we're ready to solve for our area here. So the area is going to equal the sum of two integrals. That first integral was the integral from 0 to pi over 4, and the function that defined that part of the curve was the blue function, the function r equals 2 sine theta. So we need to have, for our integral, where we have to find area, we need to have 1/2 r squared d theta, right? So that's going to be 1/2 r squared d theta. But our r here is 2 sine theta, so we'll fill that in. Plus the second integral. That second integral goes from pi over 4 to pi over 2, and a different function defines the part of the curve that makes the edge of that part of the region. So that's going to be, again, 1/2 r squared d theta, but this time our r was 2 cosine theta d theta. And you should go back and take a look at that graph and just make sure that you have matched up the right function with the right bounds on the integral. So let's go ahead and solve these integrals. In fact, I'll solve the first one here, and you can go ahead and solve the second one on your own because it's going to be a pretty similar process. I'll sort of split this down the middle here, and we'll just worry about the first integral. So let's just simplify things a little bit here. We have the integral from 0 to pi over 4 of, let's see, 2 sine theta squared. That's going to give us a sine squared theta. And then 2 squared is 4, but 1/2 of 4 is 2, so it's just 2 sine squared theta d theta. Now, because our sine has an even power and there's no cosines in here, we'll need to use the power-reducing formula. And the power-reducing formula says, let me get the integral, pi over 4, 0 to pi over 4, of 2 times, so sine squared theta is equal to 1/2 of the expression 1 minus cosine of 2 theta times d theta. Now, of course, if we had cosine squared theta instead, that's equal to 1/2 of 1 plus cosine of 2 theta. And we know that sine squared theta is equal to 1/2 of 1 minus cosine of 2 theta. So watch out here, because we are starting with a sine squared theta. We are ending up with a cosine of 2 theta in there. No matter which power reducing formula you use, you'll end up with a cosine 2 theta, but there's a change of sign there, either a plus or a minus, depending. So be careful. Okay, now 2 times 1/2 is just 1, so I can just change that to a 1 here. And we're ready to actually find the antiderivative. So the antiderivative of 1 is theta, minus the antiderivative of cosine of something is sine of that same thing, so 2 theta. And we'll have to use the chain rule in reverse, or a U substitution here, and divide by the coefficient on theta, which is a 2. So we'll have 1/2 here. And we are going from 0 to pi over 4. And plug those numbers in, so we're going to get pi over 4 minus 1/2 sine of 2 pi over 4 minus 0, and I'll put a parentheses here, and then minus 1/2 sine of 2 times 0. Now, 2 times 0 is 0, and the sine of 0 is already 0. So this guy, just go into 0. Get rid of it right away. And we end up with pi over 4 minus, let's see, well, 2 pi over 4 is pi over 2. It's 1/2 pi. That is basically a right angle. That would be the angle that's pointing straight upward. The sine of that angle is 1. So 1/2 of that is just 1/2. That is the value of the first integral that we did. So you should go ahead and try and solve that second integral on your own, but you will find, unsurprisingly, since there's a lot of symmetry in that graph, you would probably expect that the area of that other half of that region should be the same as the area of the first region, and it is. And it turns out if you do this integral correctly, you will get pi over 4 minus 1/2. So our total area is the sum of these two. That's going to be pi over 4 minus 1/2 plus pi over 4 minus 1/2. So that is pi over 2 minus 1. And that is our total area. I think it's very interesting to look at some of these problems and think about how we might be able to solve them without calculus. Could we solve this one by just pure geometry? I think we can. Notice that what we have here, we have two circles on a coordinate axis, two circles of the same radius on a coordinate axis. Pretend those circles are better than they are. Okay? They're intersecting at a certain point, and in fact, if this is 2, this is 1, the center of this one circle is 1, the center of this circle is also at, well, it's 0, 1, and this is at the point 0, 2. And this point of intersection here, because this angle here is pi over 4, means this point of intersection, the x and y coordinates are actually going to have to be 1, 1. That's the only point you can have. If you actually check the radius there, the radius, the r, turns out to be the square root of 2, which is what you get if your x and y are both 1. So what's going on here is, without any calculus, what we can say is, let's drop this down here. What we can say is, what I have is a quarter of a circle of radius 1. And if I take away a certain thing from that, I'll get a part of the region I want. If I take away this triangle that's right in here, I don't have the full region that I want, but I'll have half the region I want. So minus the triangle, the right triangle, in fact, with a base and height of both 1. That should give me half the region. So let's see if we can work this out here. So 1/4 of a circle of radius 1, that means I need to have 1/4 of the area of that circle, which is pi r squared. But our r is actually 1 here, so that's just 1. So we actually, that is going to be pi over 4 then, right? And then minus the area of that right triangle that I don't want. The base and height are both 1, and that's going to be 1/2 base times height. That's the area of a triangle, right? So our base and our height are both 1. So 1/2 times 1 times 1 is 1/2. So guess what? We already solved an integral to find the area of that blue little banana shape there, that half of the region that we want. And that integral gave us pi over 4 minus 1/2. But it turns out we could solve this by geometry alone. And our total area is again twice that. Is going to be 2 times pi over 4 minus 1/2, which is pi over 2 minus 1. That is the total area of this region of intersection between the two circles. So in this case, we could have actually solved this problem geometrically instead of with calculus. I think it's worth having the skills to solve it both ways, but it's also worth keeping in mind the principle of be lazy. Try and solve this in the easiest way that you can. Don't do extra work beyond what you need to. Look for ways to use geometry or other tools, or take advantage of the symmetry of the situation to help you solve your problems. That's always a good idea.